Hello everyone, my name is Ryan An. I am a PhD student at University of California, Merced. Today I will present to you our paper, Go Beyond Black Box Policies, Rethinking the Design of Learning Agents for Interpretable and Verifiable HVAC Control. HVAC stands for Heating, Ventilation, and Air Conditioning. It is the most energy-consuming system in almost all modern buildings, consuming about half of the building's total energy usage. In smart buildings, the HVAC system needs to solve a dual objective optimization problem to maximize the time in which the occupants are in a state of comfort and to minimize the energy consumption at the same time. As the HVAC controller gets better at solving this problem, we can save millions of dollars of energy bills per year worldwide while slowing down the rate of global warming. Currently, the HVAC controller is usually a rule-based program designed by human experts. This is what we currently have for all our buildings, and researchers have been trying to improve upon this baseline. Data-driven control method is the most promising approach. It is shown that it can save 10% of energy usage in the lab environment. It is constructed in the way shown here. At each decision step, it takes an observation, then uses a data-driven model and a optimizer to solve for the optimal control action. Although the data-driven method has been thoroughly studied for at least the past 5 years, it has not been deployed for almost any of the buildings. And the reason is that this method has a trustworthiness challenge. Before deploying them in real buildings, we want to guarantee that this controller always makes decisions that are safe, or in other words, satisfy some human-defined rules. This requires the controller to have two properties. It needs to be interpretable and verifiable. However, the current method, using the components mentioned earlier, is neither interpretable or verifiable. We noticed the challenge and decided to thoroughly rethink the entire control method so that the new method will have the energy efficiency of a data-driven method and be interpretable and verifiable at the same time. Our method is to use a decision tree as a control agent. The decision tree will take in our observation and map it directly to action. And now I will explain how we did it. So the first problem to solve is to make a decision tree agent has the same energy efficiency as a data-driven agent. Now, because the data-driven agent already has superhuman energy efficiency, the decision tree has to be automatically generated as well. The way we do it is to use the original data-driven method as an optimizer to generate high-quality decision data. So for each observation, the optimizer generates an optimized action, and the observation action pair is collected. Then, we use these decision data to automatically fit a decision tree, which maps the observation directly to optimized actions. However, if you are familiar with the field, you might notice that there is a problem. HVAC control agents need to consider a high-dimensional input consisting of all kinds of information, both internally from the building and externally from the outside environment, such as room temperature, humidity, outdoor temperature, wind speed, etc. If we want the decision tree to have an optimized action for all possible combinations of these observations, we need to first exhaustively optimize for all possible combinations of observation using the optimizer. This can be prohibitively time-intensive. We found a way to solve this as well. We looked into the data distribution from a real building and realized that the actual observation that a normal building experiences from daily operations is centered around a highly concentrated distribution. Particularly, the internal room temperature concentrated around the comfort range, and the external environment temperature follows the same distribution as the weather data. So there is no need to exhaust all possible combinations. We just have to follow the historical data distribution. The rest combinations will be highly unlikely for the building to encounter in daily operations. To balance between generalizability and time consumption, we developed a sampling strategy based on Gaussian noise addition to data distribution. The amount of noise added, shown here as noise level, is empirically determined by maximizing entropy and minimizing information distance from the original distribution from an information theoretical perspective. So with that, we solved this part. And now we have a highly efficient decision tree. The next step is to verify the safety of the decision tree. We designed an algorithm to specifically verify the decision tree. Now I'm going to introduce this algorithm. The rules that we want to verify are logical propositions defined by human experts that the behavior of this decision tree must satisfy, such as this. If input X is in certain range, then the action should also be in another certain range. Just to demonstrate this process, we consider two example scenarios. If the temperature of the room is cooler than the comfort range, then the control decision must be a temperature higher than the current temperature. This higher set point will lead the HVAC system to heat up the room, and vice versa. In decision tree, each decision node makes a comparison with one input parameter. This splits the input space with a hyperplane. Each leaf node corresponds to a region in the input space. We can find this region for each leaf node. Like so, as shown on the right side of the slide as an example. We can do this for all leaf nodes in the tree. Then, we can assert the input-output logic propositions for each leaf node. In this case, as shown on the slide, we are comparing the maximum or minimum room temperature of the input region of each decision node with the action of that decision node. If there exists a case within that region that violates the proposition, the corresponding leaf node is flagged, in this example shown on the slide. If the room temperature is between 25.5 to 23 degrees Celsius, the resulting decision will then set the temperature to 23 degrees Celsius, which heats up the room when it is unwanted. So this is how we verify a defined rule. Now, what about when there is no rule to bound it, such as in this case, when the room temperature is already in the comfort zone? In those cases, we do probabilistic verification using Monte Carlo method. The goal is to see if the decision by the decision tree keeps the room temperature in the comfort zone in the future. With this, I conclude our design. Our method is summarized here. We first use a noise addition method and the original controller to generate optimized actions. We fit the decision tree, and then we use a verification algorithm to verify the safety of the decision tree. To evaluate our method, we conducted simulation experiments with the real weather data from 2 US cities. We want to answer the following research questions. Will our method provide high energy efficiency? Does it converge fast enough? Will the tree size be within a manageable level? And finally, does it run fast enough on edge devices with limited computation resources? We compared our method with the state-of-the-art data-driven methods. The results show that our method has superior energy efficiency. Compared with the amount of energy savings generated by the state-of-the-art data-driven method, our method saves 68% more energy on average. We also observed that our method converges with a small amount of decision data and tree size. Empirically, we only needed 30 minutes of computation using an NVIDIA 3080 graphics card to generate sufficient decision data to train a decision tree that meets the converged energy efficiency level. Finally, for the inference time, our method uses more than 1,000 times less time than the state-of-the-art data-driven method. This means that our method can run on edge devices with much less computational resources. With this, I conclude my presentation. Please feel free to reach out to me if I can help answer any of your questions. Thank you.